Hi folks, welcome to this lesson on applications of definite integrals. After the last lesson we learned that the definite integral of velocity is net displacement, and that gives us insight into what a definite integral really does. It tells us the accumulated or the net change if we take the integral of a rate. So net accumulated change is going to be the integral from time 1 to time 2 of some rate function. R of t is some rate function. And to sort of work this idea through, which seems very abstract, we're, just like in our last lesson, we're going to do a question in two different ways. We're going to look at the number of bacteria in a petri dish, and it's currently 100. The bacteria are multiplying at this rate that's given over here, e to the 0.25t, where t is in days. And we'll approach these questions in two different ways. We want to find the population growth over the next 15 days, and we want to figure out the actual number of bacteria after 15 days. And each method's going to be a little better for each type, but I think the integration in the end is going to be a little nicer. We'll do it without integration, or at least without definite integrals to start with. So here's the rate. Okay. If you bump it up, then you'll get the number of bacteria. So the rate of growth, that's really number per day. Okay. If we take that rate function and we find its indefinite integral, you can see the rate's going to be in numbers per day, but the dt there means you're going to multiply sort of by days. Your units are going to just turn it into the number of bacteria. Okay, number of bacteria. So that's the indefinite integral of e to the 0.5t dt. And so that's going to be, the power will stay the same because it's an exponential. We'll have a plus c, but we'll also need a 1 over 0.25 out front. And maybe we struggle with the idea of 1 over 0.25 when we're doing this analytically. So that's the same as 100 over 25, because the IB is not going to be very happy if we leave decimals in our fractions. So the number after t days is going to be 4e to the 0.25t plus c. And now we've got to try and hunt down c. And what we know is that when t is 0, n is 100. Okay, so let's sub that in. If t is 0, we'd have 4e to the 0.25 times 0 plus c. That would all equal 100. And so we'd have 4 plus c equals 100, where c is 96. And all this stuff would let us find a good function for the number of bacteria that we have. Okay, there we go. After t days, that's what happens. We already know that when n is 0, that's going to work out to be 100. Or when t is 0, rather, it works out to be 100. The other thing we've got to figure out is, what did we get to after 15 days? So to do that, I'll have to find n of 15. So I'll go e to the 0.25 times 15 plus 96 and head off to the GDC. I type it in, get 266 to 3 sig figs. Okay, after all this stuff, maybe we can answer some of these questions. What was the growth over the 15 days? Well, it's going to be how much you ended up at minus how much you started at. So it grew by 166 bacteria. The other question is, find the number of bacteria after 15 days. Well, we actually knew that here, so we can just copy it down, 266. That wasn't too bad, but it wasn't too good either. It took a fair bit of effort. So here comes method 2. And we're really doing method 1 to show that it's not that efficient. In A, the change, so the growth over the next 15 days, change is going to be the integral from 0 to 15 of that rate function, which is e to the 0.25 t dt. And I can just head to the GDC and work that through. I could also do it analytically, but that would be misery, though it might give you some insight into some other stuff. From 0 to 15, e to the power of 0.25, I'm using x here, gives me 166. Pretty slick. There's our change. And if we want to find the number of bacteria after 15 days, we're going to need the initial amount plus the change. Okay, and the initial amount is n at 0. The change is 166. I actually don't need to do any work to find n at 0. I know we started with 100, went up by 166. So this is the amount at the end of those 15 days. Big idea here is, if you want the accumulated change, how much it's changed by, then use an integral. This method we used in method 2 is kind of the idea that you don't need to know where you started from to know how far you've traveled if you've gone, say, 2 hours at 45 kilometers an hour. It doesn't matter what the initial position is. It doesn't really matter what this c value is for us to be able to deal with this question. Here's some practice work on page 576, numbers 1 to 4. I hope this has been helpful, and good luck with the material, folks.